The key concepts from Module 11. First, we considered solids being dissolved into solution, and we made a distinction between non-electrolytes and electrolytes. So for non-electrolytes, the same thermochemical equations apply as for liquid-liquid mixtures, but there were other concentration scales that are more practical for use in the laboratory, and we looked at molal and molar and the various conversions between them. So I'll skip this one because it's pretty self-evident. Solvent activity can be determined from vapor pressure measurements, and it's by looking at variations in the solvent activity and using the Gibbs-Duhem equation that we can determine variations in the solute activity, and hence the chemical potential of the solute in solution. We looked at a variety of colligative properties: freezing point depression, boiling point elevation, and osmotic pressure. And we found them to be independent of solute identity, that's what colligative means, depending only on the number of dissolved particles. The definition of an electrolyte is that it dissociates into constituent ions when dissolved into a solution, and a strong electrolyte completely dissociates into its constituent ions. Because of that dissociation, we have to work with mean ionic quantities when we look at thermodynamic quantities, and that includes mean ionic molality and mean ionic activity coefficients. Also, because of that dissociation, colligative properties are enhanced. More things are created when a salt dissolves into a solution than when a non-electrolyte dissolves. We derived, in a lengthy process because it's not a trivial derivation, Debye-Huckel theory as a model to predict from first principles, from underlying physical assumptions, what the mean ionic activity coefficient for electrolytes will be at sufficiently high dilution, and this is the relevant equation that we derived. It involves the inverse Debye length, kappa, which is the distance where there's the maximum probability of finding a counter ion, that is an ion of opposite charge, compared to a like ion in a given electrolyte solution. So kappa depends on the ionic strength, which is shown here in parentheses, and the full definition here involves Avogadro's number, the charge on the electron, the permittivity of free space, the dielectric constant of the solvent, Boltzmann's constant, the temperature one is working at, the concentration of individual ions, this is a sum over ions, and the magnitude of the charges on those ions, 1, 2, 3, 4, what have you. Those are the key points from Module 11. Next up will be Module 12.